Okay. So we have a sixth lecture, theoretical one, on our mobile robotics course. Today's lecture is on path and motion planning. As usual, you can open slides on your device by link or by QR code. So today we're going to talk on path planning problem, what it is, and then we will discuss what configuration space is and how it is used to plan the path of the robot. And we'll discuss three different approaches to path planning: cell decomposition, roadmaps, and potential field. I'm reminding you that we're discussing this control scheme of modern mobile robot. We already had several lectures on localization itself, on motion and observation models. We also discussed mapping, how we can build maps for our robots. And today we are moving to path planning, where we already assume that we know where we are in space. So we solved the localization problem first. Now we know where we are. We have some map of the environment, and we want to plan our path through this environment. We actually, the next lecture will be the last one on theoretical part. We will discuss control algorithms, and then after the next lecture, we will move to some practical part of the course, and we will start discussing robot operating system. There still will be a lot of theory because we will discuss concepts and principles of robot operating system, but we will have some live coding on each lecture after the next one to see how to work with robot operating system. So returning to path planning, there are actually two terms which are usually misunderstood and substituted, even in professional scientific literature. Sometimes there are mistakes and people use one term instead of another. So let's first discuss what the difference between them. So there is path planning and motion planning. And by path planning, we usually mean finding a collision-free transition or path from some initial to some final configuration in some space containing obstacles. So there are many words. Let's see what they mean. We have a configuration of robot, and while speaking on mobile robotics by configuration, we usually mean pose of the robot, so position x, y, and orientation theta. But the same term applies for example, industrial manipulators, and then by configuration we can mean, for example, angles of all joints and all links of industrial manipulator of robotic arm. So this definition is general, so it applies to any type of robots, but we remember that for mobile robots, usually by configuration we mean pose on a plane. Then we are trying to find collision-free transition or path. Of course, there are some obstacles in our environment, and we don't want to collide with them, to hit them. That's why we're trying to find collision-free path. And motion planning is planning and executing commands leading the robot to follow the planned path. So in path planning, we just trying to find path itself. In motion planning, we also are trying to find commands which we have to transmit to our motors or to our steering wheels to lead robot through the environment. So motion planning is a bit more complex than path planning because we're already thinking in terms of our actuators. And there is an example. So for instance, you have a navigator in your cell phone or in your car, and path planning is when our navigator is saying that in 3 kilometers we have to turn right. This is a path planning. We know that at some point of space in 3 kilometers we will have to turn right. And motion planning is a bit more complex. Then if our navigator could tell us that we have to turn steering wheel 20 degrees clockwise and then press the accelerator pedal by 10%, this is a motion planning. So we're already speaking in terms of our actuators and our turning wheels and so on. So this is the main difference. Sometimes, as I said, these terms are interchanged even in scientific literature. So you have to always see and understand on which one authors are talking. But the thing is, many path planning algorithms also solving motion planning problems. So that is why there is this interchangeability, because there are many algorithms which solve both problems at the time. So that is why sometimes these terms misunderstood. And there are also some common terms you have to know. There is global path planning and local path planning. As a result of global path planning, we obtain something called global path or road. And as a result of local path planning, we get something called local path or trajectory. So global path planning is when given start point and end point and the map, of course, we need to find the optimal, usually optimal, not always possible, but usually we are trying to find optimal path. And in global path planning, often kinematic constraints of the robot are not taken into account while planning. For example, if our robot is a car, and we know that car is only moves on circles, on circle arcs, our global path still can be linear or polyline, even though we know our robot cannot move on sharp angles, cannot turn on sharp angles. Global path still can have these sharp angles, because then we will perform local path planning, where we will build kinematically feasible trajectories. So local path planning is when having information coming from sensors. So in local path planning, we already consider dynamic obstacles. In global path planning, we only consider map, predefined static obstacles. So in local path planning, we also find the local path, just a small part of the whole path. That's why it's called local, that is free from collisions and deviates as little as possible from our previously planned global path. So we have a global path which leads us from point A to point B, which can be on huge distance from one to another. For example, two cities. When we are planning in our car the path between two cities, this is a global trajectory, global path or road. And then we are traveling along this global path, and we always replan, because there are dynamic obstacles on the road. So if we have our navigator in car, we cannot just follow what navigator says, because there are other cars, there are pedestrians, so we have to avoid collisions. And this is local path planning. So we're trying to deviate as little as possible from global paths, and we avoid obstacles. And there is another term, collision avoidance, which is usually the same as local planning. And all three of these terms are usually used in scientific literature, in robotics books, so you have to distinguish between them. So this is just an illustration of global and local paths. If we have a global path in blue here, then really following this path becomes impossible sometimes, because there are dynamically detected obstacles which we didn't know in advance are there. We just detected them in real time with our sensors, and that's why we have to replan. This is a red line, but we still try to follow the global path as close as possible to reach the finish point. So I hope everything clear here. If not, ask questions right away. So how to realize this global local planning? Because we have to plan both global and local plan. There are many ways and many approaches known in robotics, but there is one classical and well-known approach called two-layered planning architecture. It consists of two parts. First, there is global planning. We first have a map, and you can see that map can be updated with sensory information, but for now we just have a map. And we first perform global planning. So we know that we have to move from one room to another. For example, if you're a vacuum cleaning robot, we first building global plan, and you can see that global plan is rarely updated. So it has small update frequency, because it is planned on big distances. And then we have a second step, which is local planning or collision avoidance. And here we use a lot of sensory information. coming in real time, and it is updated frequently because dynamic obstacles are moving, and we have to replan really quickly to adjust to changing environment. And as a result, here we somehow build control commands and send them to the robot. And actually, all of this is running in the loop, but just global planning has small update frequency, and local planning has high update frequency to react to dynamic obstacles really quick. So now we have to discuss some important term which is always used in path planning. It is called configuration space. What it is, let's have a vector Q. It is a vector uniquely defining the state of the robot, or we can call it vector of configuration or configuration vector. As we already discussed, configuration of a robot is a state of the robot, which can be different for different types of robots, or even for the same type of a robot, it can be different depending on the task. So for example, as we already said, we can have manipulator or robotic arm, and position of all links or joints is something we can call configuration of such robot. Or for mobile robot, which we familiar, position in space can be configuration. So these three numbers, x, y, theta, can set the state or configuration of a robot. And if we have this vector Q describing the state of our robot, then configuration space C is the space of all possible states or all possible configurations of our robot. So let's take a look at pictures. Imagine we have our robot, which is circular, green circle here. And this is a map, so you can see walls and obstacles in purple. And all configurations of our robot possible in this map are called configuration space C. And you can see on the bottom picture that configuration space can be divided in two parts. Let's see it on the next slide. So there is C free. So basically this is a free area where our robot is possibly could be. And also C obstacles. This is the area occupied by obstacles where our robot cannot be. And this both sets, C free and C obstacles, are subsets from the whole configuration space, or subsets from W, which is robot working area, the whole our map, for example. And also there are two configurations which we will call initial and goal configurations. So in tasks of path planning, we always have our current position, C initial, and then we have our goal configuration, C goal, where we want to arrive. And you can see here, the important thing is that when we have a physical dimensions of our robot, for example, our robot is circle here, our C3 becomes smaller than just a free space. Because, for example, here, you can see that our robot, since it has a real physical dimensions, it cannot move to this obstacle in purple closer than on radius of the robot itself, right? So we just cannot move closer because it will lead to collision. And that is why when we make a transition from just a map to configuration space, our obstacles become kind of bigger. You can see orange dashed line here. This is the size of this C obstacle. Because we know that our robot or our configuration cannot be inside this orange dashed line. That is why we use this kind of inflation of obstacles to make our C3 smaller. And since it is smaller, it is easier mathematically for us to plan, because then we will use different types of graph algorithms and different computational methods to construct our plan. And the smaller configuration space is, the simpler or faster our algorithms will find our path. So I hope this is clear, that our configuration space, in configuration space, obstacles becomes bigger on a radius of our robot, because our robot cannot move closer to obstacles. So if you have this configuration space, then the path planning problem is reduced to finding the set T, which is set of configurations of our robot from initial configuration to goal or final configuration. And all of these configurations, intermediate ones, have to be the part of C3, because there cannot be any configuration in our plan which will lead to collision, right? Because we want to find a collision-free path. Yeah, and since we already had this inflation, then here our robot can be considered as a physical dot or point in space, which is quite simpler, right? To work with points rather than a robot with its real physical dimensions. This is why people like this configuration space then, because performing this transition once, we then can consider our robot as a physical point. And there are just two examples. Imagine the map. Black is obstacle. Here is our robot. We know that our robot, that obstacle is static, so it doesn't move. And we know that configuration space of our robot is X, Y, theta. So our configuration space in 3D can be represented as a cube, right? Or a rectangle, where different dimensions mean different coordinates of the robot. And we know that there is some area shown in yellow which we cannot cross in this 3D cube. So we cannot choose any combination X, Y, theta inside this yellow area, because this area representing obstacle. And in this 3D volume, we can find any path which is collision free and which is joining our initial state and our desired or goal state. So kind of path planning problem turns into a problem of finding set of configurations in this 3D space. And the same applies for moving obstacles. This is just a simpler example, because the space actually should be 4D if we want to consider theta also. But here we just say that robot is X and Y, so the orientation doesn't matter for us in this concrete example. But here the obstacle is moving, and the third dimension is time. And we know, for example, we know the speed of obstacles, right? We can assess somehow the speed of obstacles and obstacle, and then we can build the configuration space like that. We can see that with time, the obstacle is changing its position and occupies different space in our 3D space. And then we have to find some trajectory in this 3D space, which is not colliding with this figure representing obstacle. So is it clear for a configuration space how it works and how we can use it? Okay, if there are no questions, let's move further. So almost any approach to path planning, now when we have our configuration space, we somehow know how to work with it, we know how to define it. Almost any path planning algorithm can be constructed from three simple steps. So first we define our configuration space, and we already discussed how to do that. If we have our mobile robot, we can choose either we want to just know X and Y and plan X and Y of robot, or theta also is important for us, or maybe speed or velocity at every point of space is also important, and then we will have more complex configuration space. So we somehow define it. Then we decompose or discretize our configuration space. We do that because we're really bad at working with continuous spaces. The computational resources are incredible and huge for working with continuous spaces, and our mathematical methods do not work well with continuous spaces. That is why we always try to discretize our space to speed up our path planning. And as you can realize, since there are moving obstacles, path planning is really time critical. So we have to plan really quickly to avoid collisions. And that is why we always try to discretize and to simplify computationally our task. And then when we have discretized configuration space, we can find the path in this space using several types of algorithms. This can be just search algorithms, which I think you're familiar with, or it can be sampling-based algorithms. So search algorithms are trying uh, to use every part of discretized configuration space. So they're basically considering all possible configuration, while sampling-based algorithms try to speed up computations even more, and they use samples from our space, trying to construct as optimal path as possible, but they're not considering every cell in our discretized space. We will see what the difference of these two approaches further in lecture. So let's consider all three of these steps. And first one is defining our configuration space. So definition, as we said, different planning problems may have different definitions of configuration space. Even for wheeled robots, which we are discussing mostly, there are many options. So for example, you remember we can have holonomic robot, which can instantaneously change the velocity and direction of motion. For such robot, the orientation is not really important because we can move in any direction immediately. That is why for such types of robots, configuration space is usually set just by coordinates X and Y. For non-holonomic robot, orientation is really important. For example, for a car, orientation is important, and that is why we will have 3D configuration space. Sometimes we want, as we said already, we want to take velocities into account because for us it is important which velocity we will have in every configuration within our path. Then we can add velocities here. And there are many more options. For example, in autonomous cars, developers consider comfort of passengers, right? So you don't want to be inside the car which has huge accelerations and deaccelerations. That is why here in our configuration space, we also can consider acceleration and then first and second derivatives from acceleration. And this problem becomes really huge because the dimensions are growing. And of course, the bigger dimensions we have, the much more computationally complex our path planning problem becomes. So first we defined our configuration space. Imagine we chose one of the options, and now we know in which space we are operating. And then we have to perform decomposition. As we said, the second step is some type of space decomposition. So we will consider three different approaches to space decomposition. There is cell decomposition, where space is split into cells. Cells can be equal or different in size. You remember we discussed something really the same when we discussed mapping. In mapping, we also discretize our space into cells, and these cells can be different shapes, different sizes. I hope you remember this. And then based on the connectivity, we build connectivity graph based on adjacency of the cells. So for example, we know that from the cell we can move upwards or downwards to the left or to the right, and then we build the connectivity graph. So from each cell we can have either, if cells are squared, we can have either 4 transitions to top, bottom, left, right, or 8 if we can move also diagonal. We know what type of robot we have. Either it can move diagonal or not. And based on this, we build the connectivity graph. And as a result of any of these 3 types of decompositions, we actually get a graph, because then as a third step, we want to use simple graph-based algorithms, search algorithms. That is why we try to make a transition from complex path planning problem to simple graph search problem. So with roadmap decomposition, we are not splitting the whole space into cells. We represent only free space. If in cell decompositions, we also consider obstacles and split the whole space into cells. In roadmap decomposition, we consider only free space, and we represent this free space as connected curves or roads. There are many algorithms to build this roads. Can discuss several of them, but you can see on the images that we just try to represent free space as a set of curves. And again, of course, these curves have nodes, and this can be represented as a graph. And again, we can use graph search algorithms to find the optimal road in such a decomposition. And there is a third type, which is called potential fields. This is a also big class of methods, big family of methods. We define potential field over the configuration space with a minimum at the target configuration. Imagine this cross is our target configuration, so we will have a minimum potential here and maximum potentials in obstacles. So what we do here, we are trying to represent our world and our robots and our obstacles as charged particles, as from physics, as electrons and protons and particles with the same sign will be trying to split apart, and with the opposite sign will have forces. So basically we define a navigation function here, and then we're trying to find the potential field in each point of space, and we will move our robot in the way so the potential field is minimum to reach our final goal. You'll see images on the next slides how it works. So we will discuss all these three types of cell decomposition. So let's start from cell decomposition. As we said, we represent the whole space, even obstacles, as you can see, as regions according to certain rules. You know that cells can be equal, as on the top image, or there can be some adaptive sampling. So bigger free spaces can be represented by bigger squares, and space close to obstacles can be represented with small squares. This gives us something that we know how obstacles look like precisely, but it doesn't matter for us how free space looks exactly, because we just know that it is free. So this is called adaptive sampling, and what it gives us is that the computational complexity is smaller because we have to consider smaller number of squares. So path planning problems, path planning algorithms will be just faster in this representation than in this one, but this representation can be more complex to obtain. We usually do it in advance. If we have a map of our environment, we discretize it in advance. So it can be not important for us that to get this representation is more computationally complex, because we do it in advance before starting moving. So then we consider adjacency of regions when we have these cells, build a connectivity graph, and then we represent the whole environment as a graph, and path planning problem is reduced to the problem of finding a path in the graph. And let's discuss shortly what finding the path in a graph means. I hope you're all familiar with graph algorithms. I hope you had some algorithmic programming course, but we will try to shortly remember what it was about. So first of all, there is uninformed and informed search in a graph. Uninformed search, or blind search, or it is also called brute force search, is a search for a path in a graph or in a state space in which no additional information is used. So we know nothing on our environment except the graph itself. And the only thing we can do, we can examine all nodes of our graph in different ways and just try to find an optimal path. And also there is informed search, is then when we have some additional information, usually given informed heuristics. And if this information, additional one, is available, it can be used to say that one node is more promising than another. So we know that from this node, it is better to move here diagonally than to move upwards somehow with some heuristic or some additional a priori information. This is called informed search. And of course, informed search is more optimal. If we have some additional information, we should use it. So there are many algorithms of uninformed search, and I hope you know some of them. There is breadth first search, depth first search, bidirectional, limited depth, uniform cost search, and many. There are many graph algorithms known. They all have different complexity. They all optimal in different situations. So this is a big separate topic of discussion. So we will not go into the details here. So we will just discuss a couple of them. So just to get a taste of what it is. I hope you know these two. These are the most simplest graph search algorithms, which are usually discussed in any algorithmic course. So breadth first search is when we have a graph or a tree. Here in this example, we have a tree. And we first consider nodes on one level before moving to another. So if we are talking on this decomposition, imagine we are in C init and we have several nodes to move first, right? We said that we can move upwards, to the right, to the left, and down, for example. So we will first consider all four options, and only after that we will move to the next level, and for each of these options we will consider four more options or three more options, because one is where we came from, right? So this is a breadth first search. So we are moving kind of wavily through this graph and considering all possible moves on all steps. So on each next step, we first consider all moves, and then only then we move to the next layer. And in the depth first search, vice versa. We first go as further as possible through one branch of this tree, or if we first chose to go up, we will first go through all combinations connected to this move, and only then we will return to our root, to our first step, and we'll consider all combinations to next step. I hope it is clear. And it is known that this type of search, breadth first search, is actually optimal uninformed search algorithm if all nodes or actions have equal cost. So if we know nothing, if we don't have additional heuristics, we can perform breadth first search, and it will give us an optimal path. Yeah, there are also modifications. We saw that there are many uninformed cost search, many other types of algorithms, and uninformed cost search is just a generalization of this one. The same idea, but for nodes having different costs. So what it does, and it basically on the same level, it actually considers which node has smaller weight if a graph is weighted, and first moves to this direction. This is the whole idea. Yeah, what it is also said on the slide. It visits nodes in ascending order of path cost from the root start node. And it is also almost equivalent to Dijkstra algorithms, which is really famous. I guess you're also familiar with it. You can read, here is a link. You can read after the lecture what Dijkstra algorithm is. And then there is informed search, and the most popular in robotics algorithm for graph informed search is A star and its modifications. There are many modifications of this algorithm, and it is really used in practice a lot. We will discuss shortly the basic version of A star, but there are many really smart modifications people came up with to use it for different situations in different environments, and it is really widely used in robotics for global path planning mostly. So let's see what it is. So as we said, it is informed search, so we have some kind of additional information or heuristic here. So the priority of the vertex or of the node to be traversed is determined by the sum of two members. First, there is a G of V of vertex. V is a vertex of a graph. So G is the cost of the path from initial state to the given one. So imagine we have our initial state here, and we are considering now this state. So the path from initial to this one is the cost to travel to this vertex. So this is G, really simple, just the cost of path from our initial or current state to this one. And H is a heuristic estimation of the path cost to the target vertex. So again, if we're considering now this cell, we have to know the cost of moving from this cell to the goal cell. And this is our additional heuristic. And this is kind of logical that the cost of this cell consists of two parts of cost of moving from initial state and from cost to moving from this state to the goal one. But this is not the real cost. This is just an estimation, just a heuristic. We will see that this heuristic for A star to be optimal has to have a special property. So this H of V have to be smaller or equal of exact cost of the path to the target vertex. What it means for us? It means that if we can guarantee that our heuristic is smaller than the real cost, then A star will find an optimal path. So here it is says that usually Euclidean distance or L2 norm is used as this heuristic. What it means? So imagine we have this map, we have it in advance. And for example, we know that we want to move to this goal configuration or goal cell. So in advance, for each cell, we can find the Euclidean distance to this cell, right? Just by measuring straight lines. So from you have to understood that this is just Euclidean distance on a straight line. So it doesn't matter if there are obstacles, we still will have a just Euclidean distance, a straight line here, right? To measure the distance from init to from C init to C goal, or for any cell, from any cell to C goal. And this will be our heuristic. So we will compute it for each cell in advance. And it is guaranteed that this distance is smaller than the real path, right? Because for any free cell, it will be just equal to a real path. But for any cell behind the obstacle, it will be smaller because we will, in real life, we will have to make a turn around obstacle first to reach the goal direction. And that is why it is guaranteed for Euclidean distance, which is measured just a straight line, that is either equal or smaller than exact cost or exact path to the target vertex. And that is why usually Euclidean distance is used for this heuristic. And G is just a cost of path from our initial state to some state we are considering. So I hope this algorithm is kind of clear. There is an illustration how it works. So you can see that A star is good and much better than algorithms of uninformed search, because to find its path, it doesn't consider all cells. So if in breadth first search, we could possibly consider all the cells in the whole map, all the cells to find the path. In A star, we usually do not consider all cells before we find a path. And a path is optimal if we satisfy this condition on heuristic. So A star is guaranteed to find the optimal path. So here you can see a complex environment, and you can see that there are many cells we didn't even consider, and it is good because that means that we found our path really fast. And here is a much smaller example where we have single obstacle and our goal position or goal configuration behind the obstacle. And you can see how A star discovers or searches the environment. And once it found it pass around obstacle, you can see that it moves really quickly to the our goal configuration. And the same here. So Since A star is a really simple but powerful algorithms, there are many configurations and modifications of A star, and there is a whole family algorithms which um, broaden the idea of A star. For example, there is a D star algorithms, or even it is not an algorithm, it is a family of algorithms which can take into account dynamic information and replan paths according to dynamic information. So here A star only uses information from map, only uses information on static obstacles, right? And that is why A star is usually used for global planning, because we remember that in the stage of global planning, we do not consider dynamic obstacles, obstacles we detect in real time. We only use a priori or prior information on our environment. And that is why A star is usually used for global planning. And you can actually, you can also see that here A star gives really sharp paths with sharp turns. And of course, we then will have to smooth this path in local planning. For example, if we have a car, if this plan is obtained for a car, of course, car cannot turn this way. We will have to perform local planning and find more smooth paths. So we were discussing D star. It can take dynamic obstacles, and the cool thing is that it uses prior information. It already discovered some space, and if there are new information, new obstacles, it doesn't start to plan from the scratch. It reuses information it already has and just changes the weight of nodes around obstacle and then further away to the goal point. So the cool thing is about D-Star is that it doesn't have to replan the whole thing if there is new obstacle. It uses in plan it already had and weights of different nodes it already had and just replants the part which get new obstacle. There is also theta star family of algorithms which can plan on arbitrary direction, which is also important. Again, let's use this illustration. So you can see here that each node has only 8 connections, right? We can move upwards, downwards, right, left, and diagonally here. But imagine that we want to connect this node and, for example, this node. Of course, we cannot do it with 45 degrees line, right? But why cannot we move this way? It would be optimal maybe in sometimes. It is not always really optimal to move 45 degrees, and not all robots move only 45 degrees right, left, up and down, right? We know that holonomic robots can move in any direction. So theta star, what it does, it says that we can, in this our graph, we can connect any cells which are on a straight line and do not have obstacles between them. So if this node and this node, these two, do not have obstacles on their way, so why don't we connect them and move just straight? This is what theta star makes this modification to A star. There is also lifelong planning A star and many more algorithms. So as I said, this is a really common and wide used type of algorithms. And if you're interested, there will be a link in the end of the lecture in which you can read more on A star and its modifications. So that was a cell decomposition. Once again, we decompose our space into cells, both free space and obstacles, you can see here. And then we built a graph based on an adjacency of these cells. And adjacency is determined on how we can move from one cell to another. Either we can move diagonally or not, and so on. And then we just use simple graph search algorithms to find a path in such space. The second type of decomposition is roadmap decomposition, and there are many algorithms to perform it. And the most important difference here is that we only consider free space here and decompose only free space, so we do not consider obstacles. And that is good because our space or our graph becomes smaller. So if here we had a graph which also had all cells inside obstacles, here we will have graph which only considers free space. So this is an advantage. And then again, adjacency of regions is established after the decomposition, connectivity graph is built, and again, simple graph search algorithms are used. So we already discussed which search algorithms can be used, either A star as an informed search or algorithms of uninformed search, such as breadth first search and many modifications. So let's see how we can get this roadmap decomposition. There are many algorithms, which we'll discuss just simple and well-known ones. So first of all, there is algorithm called visibility graphs. This is a really old algorithm. It was invented in Stanford for robots, by the way, I think in 60s or something. And the idea is really simple. Let's take our start and end points, our C initial and C goal, and all corners of our obstacles. So you can see white dots in corners of all obstacles. So we will get this set of points, our initial goal state and all corners of obstacles. And we will say that this is the vertices of our graph. And there is an edge between any two vertices if one vertex is visible from another, which means there is no obstacle on the way. For example, these two vertices are connected, right? Because there are no obstacles on the way, but this one and this one cannot be connected directly because there is an obstacle on the way. And that is how we build a graph. And on the image, you can see an example of such a graph. So you can see that there are many connections we can perform even in such simple environment. And all vertices are connected with initial configuration if there is a visibility between them, and the same for final. And then we just use any available graph algorithm to find the path in such a graph. So here it is shown in orange, our optimal path in such graph. And you can see that it really allows us to move from initial state to final state. Of course, it is suboptimal, but still we found a path which is collision free and we can use it. The complexity of building such graph is n squared log n, where n number of vertices. So it is quite kind of complex, but still. And there is one main disadvantage of this algorithm. You can see that our path, since we used edges or corners of our obstacles for building the path or graph, our path is lies along the wall, basically. So to really use this path to travel from C initial to C goal, we have to modify it somehow. So we have to move it away from wall, at least on the size of our robot, right? Because we cannot move directly along the wall. We have to modify path somehow. And here, of course, we cannot move to the corner directly. We want to move somewhere here and then perform a turn. So after finding a path in such graph, we still have to perform some modification to this path. And this is the main disadvantage. So there is also approach called Voronoi diagram, or based on Voronoi diagram, because this is a mathematical method which is used in many problems. So what is Voronoi diagram for plane? It is a decomposition of space into the elements in such a way that points lying within one area are closer to some point within this area than to any other area. So there was an example, but I think the link, I just want to show you how it is built. Let's see. Yeah, this one. So this is just an interactive Voronoi diagram generator. So imagine we have one point here, and then of course any point in this plane are close to this, considered close to this point. But as soon as we have second point, every point in blue region is closer to this point than to this point. And every point in orange region is closer to this point called seed to then to this point. And we can continue infinitely splitting this space into regions, and every point in region colored in one color is closer to this seed inside this region than to any other seed. And this is a really useful decomposition. It is used in many real life problems. In robotics, and can be used to partition the space in the following way. And as seeds, we use actually corners again of obstacles. At least we can use, not necessarily, but we can use corners of the obstacles as seeds. And then splitting the space, we can build a path lying on the sides of these regions. For example, here, there are sides of these regions, and we can build our path on the sides. And if these points are obstacles, we know that these lines, these edges of the regions will lie as far from obstacles as possible, because we know that all points in this region are close to this point, and all points in these regions are closer to this point. The points on the line splitting these two regions are the most distant from both of these points. And if these points are obstacles, we know that this line is the most distant path from both obstacles. So this algorithm allows us to build the most the safest path, because this line is on the maximum distance from all possible obstacles. And this is a really good property, because in our path planning in algorithms, we want to consider usually several things. We want our path to be the shortest one, of course, because we want to travel as fast as possible. And we also want it to be the safest one. We want our path to be as far from obstacles as possible. And Voronoi graph gives us the second property. And actually it is optimal for being as far from obstacles as possible. And there are also many algorithms for building this representation of space. The naive algorithm is n to the power of 4, which is really a lot and really slow. And there are also best algorithm, which is not always applicable. It is applicable for some special cases, but it is really fast. You can see that it is n log n algorithm, so we can, for some cases, we can get this representation really quickly. So Voronoi graph is also really used a lot in path planning. There is also really cool approach, which I personally love a lot, called state lattice based methods. What a state lattice is that some, again, representation of space, some actually way to build a graph, to have a motion primitives, and then plan our path in or from these motion primitives. So let's see, we discretize the space in such a way that transition between the nodes are obviously kinematically reachable. Our transitions here, you can see the black is actually the resulting path of the robot. The whole space, there are no obstacles in this example. So the whole space is discretized using this set of primitives. So these are passes from any arbitrary point, our robot. In this case, I guess this is a car, because a car moves on such circular arcs. So from any point, our car can take several maneuvers. It can move along this maneuver, along this one, it can move straight, and the same to the left. You can see this is a set of maneuvers. And just by copying this set of maneuvers all over the space, we get a picture like this, which looks really complex. But you can see inside are exactly these maneuvers. And then connecting them. So for example, we perform this maneuver, and from here we can again perform one of these maneuvers. First of all, doing that, we discretize the space. So because there's a limited number of maneuvers, we can have a graph which is not that big. From any point to any, we can perform several types of maneuvers. But we know in advance that every of this maneuver is kinematically possible. This is a really cool property of this algorithm. If here we get something, you can see really sharp turn, and we know that car cannot turn 90 degrees directly, so we will have to smooth this path somehow. Here we get right away the kinematically feasible path because we build it from kinematically feasible primitives. And what especially cool is that we can store motion commands for each of these primitives in our memory, and building this path, we don't have to perform motion planning. You remember that motion planning is planning commands we will give to our motors, to our steering wheel. Here, knowing that we need to perform such maneuver, we can just take from our memory, from robot memory, commands to our motors and to our steering wheel, which we need to perform to move this along this maneuver, and directly send it to our motors and to our steering wheel. And that is why this method is really, really computationally efficient, because we have the small number of primitives which we store in our memory in advance. We compute motion commands for each primitive in advance, and then we just build our path through this graph, and we already know what to command to our motors and our steering wheel to move along this path. And that is why this method is really fast and really cool. Of course, the path is suboptimal again, because we just chose from a limited set of primitives, and maybe there was optimal path which lies somewhere here in some situation, but we cannot take this. We will move along this one or move straight, but still this is really fast method because everything is computed in advance and stored in the robot memory. Okay, there is also these were deterministic algorithms, so everything is deterministic here. There are also probabilistic roadmaps we can use. So as we said, our configuration space can be huge, and sometimes we just don't have time and computational resources to discover the whole configuration space to find optimal path. In these cases, we sometimes want to use probabilistic sampling. You remember we said that there are sampling methods. So these are the methods. So sometimes we want just to use random sampling from our space, just trying to find as optimal path as possible, because we know we don't have time to consider every cell of our space. We will just take random. So there is a description of such types of methods. So we take random samples from C3. Then we closed samples are connected to each other by an edge, provided there is no collision on the edge. So imagine we took this random sample, which is in black here, took this random sample, and we are joining them with edge if there is no obstacle between them. For example, between this one and this one, there is obstacle. That's why we do not connect them. And by taking random edges, we can build some graph like this, and then we can build a path within this graph. Of course, it is suboptimal, but we can get it really fast because we just took some number of random samples and then used them to build a path. And the proximity of nodes can be determined in different ways. So what we didn't say here is that we connect close samples, not every sample, but close, and proximity can be defined in different ways. For example, all nodes in a fixed radius. So for example, if we took new sample, we search some radius, predefined one around it. And if there is another sample within this radius, we connect them if there is no obstacles, and so on. Yeah, and the path in the resulting graph is searched by any search algorithm, any graph search algorithms. And there is a really well-known and famous and widely used family of algorithms built on this principle called rapidly exploring random trees, RRT. You can see it in robotics literature a lot, RRT. And the main idea, there are many modifications to this algorithm. You have to understand that there are many research ongoing on how to make this family of algorithms better, but we will just discuss a basic idea here. So rapidly exploring random trees. The main idea is to explore space more efficiently. As we said, we take random samples. So the essence of the algorithm is the following. Initially, we have our initial position, C init, in black here. We generate random node again from free space. Imagine we generated this gray node, and then we connect this randomly generated node to the nearest tree node. In our case, in the starting point of time, we only have C init, so we will try to connect this node to C init. But we connected if it is possible, if there is no obstacle in between, of course. But if there is obstacle in between, and you can see this situation here, there is crand, a newly generated node, and there is cnear, the closest part of our tree which is already built. If we cannot connect it directly because there is obstacle on the way, we take a new sample here on this line, the closest sample to our tree, which is not crossing the obstacle. You can see here that if an edge passes through an obstacle, then we leave the maximum part of the edge, C near, C new, C near, C new, that does not intersect obstacles. So even if we generated a kindly bad node, which is cannot be connected to our tree, we still try to use this situation and generate new node here, which is not crossing the obstacle, and we still try to expand our tree. And that is how step by step we are trying to build our tree like this. And then again, we use our search algorithms to find the path here. And we stop building the tree by the following rule. Every some iteration, for example, every 10th iteration, we take C goal as C rand. So we are not just randomly generating new sample. We are taking C goal, and we see if we can connect it to our tree. And if we can connect it on this step, then there is already path in our tree, which we can take to travel from C init to C goal. If we cannot connect C goal to our tree, then we repeat this procedure and trying to expand our tree more and more to discover more space. So with this algorithm, we really rapidly explore space. That is why it is rapidly exploring random trees. So we are taking random samples and our tree grows really fast. And then we can try to find paths inside our tree. Of course, it is suboptimal. Of course, it has sharp turns, but we can really quickly explore huge configuration spaces. So this is a really fast algorithm. So that was about roadmap decomposition. Once again, we are trying to represent a free space with some roads and then find the path within them. We can use rapidly exploring random trees. We can use state lattice. We can use Voronoi diagrams. We can use visibility graphs. And there are many more algorithms doing the same thing. And there is a third type of algorithms. We will discuss it really shortly. You can read more about it after the lecture, which is called potential field based methods. So the main idea here is that we introduce navigation function f. This function can be computed for any point in space. So for every cell here, for example, we can compute this navigation function. And this function indicates the direction to the target point from any current robot configuration. So for example, if there is a goal, to move to the goal from this point, we have to move upwards and our potential field will direct upwards. To move from our you can see that if there is obstacle, our potential field will show the way around the obstacle to move to the goal, which is logical, right? And this is reached because obstacle has a positive sign, and our robot also has a positive sign, and that's why obstacle will push our robot away from itself, given this potential field function, navigation function. And our goal will we'll point our robot to itself because they have different signs. Our robot has plus, goal usually has minus, and they as charged points will be trying to reach each other. I hope it is clear. Yeah, and here, like formally, mathematically, we can compute gradient of this potential field in every point, in any point, and this gradient will indicate the direction to our target point for our robot. And usually F is set in such a way that obstacles push the robot away while the target attracts it, as we already discussed. And this sounds quite complex, but in reality, what we do in any point of space, we just compute some vector, and our orientation in this vector indicates the direction where robot have to move to reach our goal. And obstacles are pushing our robot away, and goal is attracting our robot. This method has a potential drawback. For example, if we have an obstacle in the shape of a square, there is a minimum of our potential field, and this is kind of a situation where our robot cannot move from this obstacle and it will be stuck. So there are also modifications to this potential field method when robots sometimes move just to random direction just to avoid these minimums of potential field. So you can imagine the situation that this potential field, our goal is usually a global minimum, but it can have a local minimums, and sometimes if robot falls into this local minima, it can be stuck. So we need to find some modifications to this classical algorithm to make our robot unstuck and to move somewhere to the goal. So this is just a basic idea of potential fields. We will not discuss it into details. And that's basically it for today. What have we missed? We actually missed a lot because path planning is a huge topic. There are a number of articles, like thousands of articles written every year. So it is not a closed problem. There are still many research ongoing on path planning. So there are a huge number of improvements and extensions to the basic methods we discussed. So as we said, there are thousands of modifications of A star, of randomly exploring random trees, of potential field method. There are many modifications, and there are every year papers written on that. Also, there are local path planning methods based on different types of curves, of polynomial planning, Clotoids, Bezier curves, Dubin's path, and many more. There are the whole family of algorithms based on just using some geometrical curves to build a path, and we didn't discuss them. And also, these geometrical primitives can be used in any of these discussed planning algorithms. For example, in A star, there can be modification when we move on circular arcs and so on. So we didn't discuss it, but you have to know that there is such thing. Also, there are becoming popular optimization-based planning methods. So sometimes we are not just using graph methods to find the path. Sometimes we solve optimization problem, and it can be multi-criteria optimization problem, because we said that there are many criteria imposed on our path. We want the path be the shortest one. We want the path to be the safest one. Sometimes there are additional criteria, as we said, that it have to be comfort for passengers. For example, we have to consider acceleration and derivatives from acceleration, and there is a trade-off between all of these criteria. So the path planning can be considered an optimization problem and multi-criteria optimization problem. And there are also dynamic programming techniques or Markov decision making. This is already close to reinforcement learning. For example, the path planning problem can be considered as a reinforcement learning problem, where obstacles give us a negative reward, and free space and reaching goal give us a positive reward, and then we can use dynamic programming to find the path from any given point of space to our goal point. And it will look somehow close to potential field. So from any point of space, we will find the direction where we have to move our robot to reach the goal. There is also approaches based on dynamic programming to plan the path. And there are many more. As I said, this lecture is introductory, mostly to give you an overview of path planning problem, but there is many, many more, and there are people who devote their lives to study path planning and who read theses and scientific articles just on this topic. So that's it. There is one thing I wanted to show you. There is, as usual, additional resources. There is really good one in Russian for Russian-speaking students. This is the overview of modern planning methods, and many pictures in this lecture are from this source. But in English, there are also really, really good books and lectures, presentation. You can check. There is one for A-star, if you want to go into details of A-star. And the one thing I wanted to show you, it is actually on Piazza. You can find it there, not only for path planning. This is a, here, just a second. Nope, nope. Maybe it just moved. Yes, so here's a repository on GitHub called Python Robotics, and it is really cool for studying robotics algorithms, different ones, not only path planning. So what the guy did, it just made a collection of different robotics algorithms, and he provided a simple, really simple and naive and straightforward implementations of different methods in Python. So you can choose the topic you're interested in, for example, localization, and there will be several localization algorithms, for example, particle filter, Kalman filter, everything we discussed. And there will be simple implementations in Python of these algorithms. And here are cool GIFs about each algorithm. For example, this is a Kalman filter. There is a particle filtered localization. You can see particles here, and you can see landmarks which robot is detecting, and based on this landmark, robot is determining its position. Mapping, you remember raycasting grid maps, we also discussed it. Many cool algorithms. And there is a section on path planning. There is dynamic window approach, something we didn't discuss, but this is a really popular algorithm also. But there is Dijkstra algorithm, for example, you can see this is a graph, and there is Dijkstra algorithm on graph. There is A-star, you can see how they different, and you can see how A-star is faster because it doesn't consider the whole space. It tries to move to pass as quickly as possible, and you can see once it will move really fast once it moves around the obstacle. There is potential field, so in colors there is a potential, and you can see that there is small potential in light blue in goal position, and bigger potential here because it's the direction against the desired direction. And you can see that obstacles impose the potential which is pushing away our path. So this is a potential grid method. This is a state lattice which discussed. You can see different patterns we can take, and there is a for road, for lane moving. So this is a state lattice. You remember which when we built our passes from predefined motion primitives. So this is a probabilistic roadmap. Also, we discussed where we randomly put samples in our space. We just generate random samples, generate, and then we just try to find paths based on our random samples. Rapidly exploring random trees, you can see that we expand our tree until we can reach our final goal. And there are some modifications to rapidly exploring random trees, and there are many more. So just try to check this repository, see GIFs, see code, and you can find a lot of interesting on path planning here and on different other topics of robotics. So are there any questions?